So last time we learned about different ways to project one view of the object that looks 3D, yet you do it on a 2D piece of paper. We learned about axonometric projections, we learned about oblique and perspective, and we practice on isometric. Now this time we need to focus on, instead of one 3D view of the object, we do basically several 2D views, each one for an object seen from a different angle. So we call it multi-view instead of single views, multi-view, and it's orthographic projection. So this is the one, as I told you, that we are going to add dimensions, tolerances, and the rest of info. We add a what we call a title block and add the necessary information to it, and then this is the one that we will send to the manufacturer. Okay, now when we create this, there are standard views and non-standard views, and we'll talk about them. And also we need to make sure that when we put the dimensions, we show the location and the size of every single feature of the part, and whether they are visible, hidden in that view, if there is symmetry in them, and every single detail should be completely transferred to the manufacturer. So if you remember, the way to create these views is we put our object of interest, here this green object, we put it, assumingly, we don't really need to, but assume that we put this inside a glass box. And then you project your object, any point on your object, especially the boundaries, onto the 6 faces of this glass box. Right? Or in other words, you view the object from the front, the back, left, right, top, and bottom of the box. So you are going to get 6 views. And now if you unfold this box and lay all of these 6 views on a flat piece of paper, you will get this kind of arrangement, right? So if you put the center view to be the front view, then above and below that you have top and bottom, to the left and right of that you have left and right, and to the left of the left you have the rear view, or you can say to the right of the right you have rear view. So these are the 6 views. We call them the standard views, and you probably just looking at them, first of all you see there is an arrangement. So the top view is always above the front, it's not to the left of the front. Or the right view is to the right of the front, it's not below the front. Okay, so first there is an arrangement. Second, you see that there is redundancy. For example, you see top and bottom view almost identical. Left and right almost identical, except for some visibles are invisibles, and vice versa, and the same for right and rear, front and rear. So we really do not need to keep all of the 6 views. Every pair of them has one redundant. So what we do is we try to keep 3 of them, and then what? We'll throw 3 others away because they are redundant. We highly avoid redundancies when we do drafting. So out of the 6 views, what we do in the ANSI system, the projection method and the method for arranging these and putting them next to each other, we call it third angle projection. And in the third angle, we throw away left, rear, and bottom, and we keep top, front, and right. So we only keep these 3 views. And as you see, there is this L-shaped arrangement between them. Always the center view is the front, above that is top, and to the right of that is the right view. Okay, so we always keep this arrangement, and that's what you see when you go to your homework, right? If you go to Canvas on assignments homework 1 and you look at this, you can see for the first page, for each problem, 3 views are given to you except for this one. So this is always your front, this is the top, and this is the right. And then from these and the dimensions, you are going to create an isometric view of the object on the right side. Now, sometimes not all three views are given, only two are given instead of three. Sometimes maybe even one. Why is that? First, because the object is too simple. So two views are enough to reveal all of the features of the part. You don't really need three features. So here, actually, one of the views is missing, or it's just eliminated, because there was the belief that you don't really need it. It is actually quite similar to the front view, just a little bit stretched. But which view is eliminated? So pay attention that we never eliminate the front view. Front view is the center. We try to keep it. So we try to typically avoid top or right view, and in this case, because of the arrangement that is horizontal, you can see that the missing view is what? True, it's the top view. So in this example number 2, the top view is eliminated. And in class, I'll draw it for you, or maybe I do it today during this video lecture, but remember that there is a top view here that is eliminated. For the rest of them, that's the same. And in the second part, the isometric is given, and you are supposed to create those three views for it, right? These three guys. Now, pay attention. When you want to draw these three views again for the second part of the homework, let's say for this object, do not, and it says, put them in the standard L-shape arrangement, okay? Do not eliminate the arrangement. So do not lay all three of the views horizontally arranged or all three of the views vertically arranged. Make sure always put the three views in this L-shape format, where the top view is exactly above the front and the right view is exactly to the right. So these two are horizontally aligned, these two are vertically aligned. And that's why I gave you two problems in the first page, two problems in the second page, so that you have enough of space to keep the L-shape arrangement. So please do not eliminate the L-shape arrangement, okay? Do not make all horizontally or vertically aligned. Never do that. In this course, for sure, you would lose credit. And if you do it later, it will look so badly unprofessional. Okay, so as I said, the top and the front view are right above each other. So using that, you can transfer dimensions. What does that mean? So here, for example, if you look at this plane here, this guy, right? So this is a plane, this is a surface, flat plane. And you might wonder, how does this plane look like? Is it basically parallel to your view, or it is at angle? So if you transfer the left and the right boundaries of this on the top view, you see that the corresponding feature to this plane is this inclined edge. So this is a plane that if you look at it from the front, it would look like a plane, but if you look at it from the top, it would look like what? An inclined edge. So this is a plane that is basically at angle with respect to the front plane, okay? So this projection that you see is actually a little bit smaller than reality. So it tells you how the plane is positioned in the space or oriented into the space. You can do a similar thing here between front and right. So here you see there are two hidden features, two cuts, right? And you might wonder which one of them is which. So if you transfer the top and the bottom boundary of the small hole, of the small cuts, you see that's this guy. And the bigger one is the bigger circle. So now what does that reveal? It means that because if you look at the right view, you don't know which one of the circles is on the front, on the right face, and which one is a little back behind. But if you look here, you can find it. That the big circle is cut right from the front right plane, and it went a little bit in, and then after that, on that new plane, you have what? The smaller hole, which is cut all the way to the left side of the object, right? So it tells you which one is forward, which one is backward. So transferring dimension is extremely useful. You can even go from the top view to the right view or vice versa, but this time you cannot just use vertical lines or horizontal lines. You have to use a combination. So you have to go vertically, then at 45-degree angle, then horizontally. Okay, for example, here you might wonder that inclined plane, remember this inclined plane, we talked about it, this guy? Which one of these two rectangles here in the right view, which one of these two correspond to this plane, this surface, right? Because this surface is a kind of surface that has angle with respect to the front and right. We call it a type 2 plane. Let me show you. We call it an inclined plane here, like this blue one, but it's not like that. It is tilted with respect to the right plane. So let me draw something for you here. So if this is the cube that you have, the glass box, so this plane is something like this red plane. Okay, so if you look at it from the front direction, you would see the projection of that onto the front view. So you would see this guy. If you look at it from the right direction, you would see the projection of that on the right plane, which is this one. Both of them smaller than the actual plane. If you look at it from the top view, then you would see the projection of that onto the top plane, which is just this edge. Okay, so that's the type of plane you have here. We call it the plane type 2. Now, as I said, so in the top view it's an edge, in the front and right it's a surface. Now you might wonder which one of these two rectangles, because we know one of them belongs to this because we can transfer horizontally. So one of these two belongs to this one, but which one? Is it to the left or to the right? So this is what we do. We know that this edge belongs to this plane, so now I transfer the boundaries of this inclined edge to the right view using horizontal, 45-degree, and vertical. And if I bring them down, you see that it is actually what? The one on the left. So the one on the left corresponds to this one. Okay, so transferring dimensions can be extremely useful. Now, before I go further into detail, let me actually, I don't need this. I would like to talk about different types of planes. Okay, categorization of different surfaces or planes. Then we go into more details. So there are three types of surface or plane that we have to recognize. The first one, which is the easiest, the best one, we call it a normal or a parallel plane. That's the type of plane, like this blue surface here, that is parallel to one of the main three directions. Either is parallel to the front plane, or parallel to the top plane, or parallel to the right plane. So it's parallel to one of the planes and naturally perpendicular to the other two. So let's say it's parallel to the front. So how does it appear? In the front view, since it's parallel to the front, it appears full size, completely equivalent to the actual surface. How does it appear on the top and right? It appears as an edge, either horizontal edge or what? Vertical edge. Okay, so we call this plane type 1, or we call it a parallel surface. Plane type 2 is an inclined surface, something like this guy here. It is not parallel to any of the main three directions, but it's perpendicular to one of these directions. Now here, if you can see, this guy is perpendicular to the right plane. So on the plane it is perpendicular to, it is appearing as an edge, but an inclined edge, not horizontal, not vertical. And on the two other planes that it is neither perpendicular nor parallel to, it appears as a plane. Both of them are smaller than what? The actual size. Finally, we have the oblique or type 3 plane. This guy is the worst because it's not parallel, not perpendicular to anything. So on all three views, it appears as a what? As a surface, basically, as a plane. All three of them are what? Smaller than the actual size. So here, just to practice before we get any further in, here is an object in green, an isometric view, and I provided the names to each one of the faces, okay? Actually, there are a few more, but here, let's just focus on these 7 planes. As I said, there are a few more, one here, one here, one here, one back there, several back over there, and this one. But if we just look at the 7 planes, we want to identify which one of them is plane type 1, which one 2, which one 3, which one... we don't have a 4, right? So 1, 2, or 3. So let's do that practice together. So here, if I put them right here, and we create a small table, so we want to know which one is a parallel plane, which one is an inclined or type 2 plane, and which one is an oblique. So if you look at A is clearly parallel to the top view, and in the other views it is appearing as an edge. So A is here, this horizontal edge. Here A is not shown, but if you show it, actually you need to have some hidden lines, and those hidden lines will show A. So A is a parallel plane. B, as you can see, is not parallel to anything, but it is inclined and perpendicular to the right view. So in the right view, it is appearing as an edge, but in the top view and in the front view, it is appearing as a plane smaller than real one. So it is this one. C is the same situation, but it is perpendicular to the front plane. So if you look in the front, it is an edge, but in the right, it is this surface, and on the top, it is this one. So C is also an oblique. D is perpendicular to the front, so it comes here, and you see in the front view, it is a surface, but on the top, it is a horizontal edge. On the right, it is a vertical edge. E is parallel to the top view. So in the top view, it is a surface, and on the front view, it is a horizontal edge, and on the right view, it is also a horizontal edge. And finally, no, F is an oblique plane. On all three views, it is appearing as surface here, here, and here. And H is parallel to the right. So here on the right, it is a surface. Here it is a vertical edge, and here it is also a vertical edge. Okay, so this is how you categorize different planes, and that will help really too much when we go to draw the three views of an isometric. Okay, so now let's practice it. So here, let's say I have this guy, and I want to basically create the three views of that. Okay, so here, now when we want to do it, especially for homework problems, now this one is just approximate, but for homework, our isometrics are all given on grid, so we exactly know the dimensions in each direction. And then next to it, we also have what? Orthographic or engineering paper, on which we draw the three views. Both of these papers, as I said, are available on Canvas. So if you go on Canvas under modules, you can have both what? Under assignments, you have orthographic projection and isometric, right? So we can have both of these guys. Now, in order to make this practice a little bit more accurate for you, I will add a little bit of engineering paper to my Microsoft OneNote, so that when we come back here and practice, can do a better accurate job. So as you can see, this guy here, I have not provided dimensions for it. I have not created it on an isometric sketch paper. So let me try to do that here on an isometric. So I redo it here with dimensions, so that when we want to create the three views, we can do it accurately. So instead of this just being drawn on the blank paper, I'll try to do it here, but with some dimensions. So I'll decide some stuff, like for example, I decide this bottom one to be like 7, 6, 5 could do the job. This one can go 2, 1, 3, so 6. Maybe this one 8. 6, 8, and 5. Okay, so let's go with 6, 8, and 5. See what happens. So we start somewhere and we go 8 units. So if we start here, so 8. Hopefully my pen works just fine. Okay, so we go right. So 1, 2, 3, 4. I cannot make it. How about here? So 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. No, I made it 9, so I don't need to go that far. Just 8, I guess, should do the job for me. 2, 3, 4, 5, 6, 7, 8. So let's say that's the bottom edge. Then in this direction we go 6. So it comes to here. And then we need to go. Let me move this temporarily somewhere else that I can see. So this one, as I said, we go up 1 unit. And then let's make this like that. This one we go 2 inside. I'm going to connect. Then we go 2 up. Then we go, that was 1 and 1, so here we can go 2 and 2 to keep the same slope. Remember that it's all one plane, so you have to keep the slope the same. And then here we go all the way back, and this we just go parallel to 1 and 1, so we go like this until we reach here, right? Okay, and then let's say this one is a 2 by 3. And the height is also 2. Okay, so here I made this object with an isometric paper. So now when I want to come and draw the 3 views of it, I exactly know how far I should go. Good. Now what? Now, just for the sake of practice, what we do, we give a name to whatever surface that we can see. So I call this top one A, this one B, C, D, E, F, G, and H. Okay, so here I can see basically 8 planes. And remember that this direction here is your front view. This direction is your right view. And if you look from the top, as you are staying on the front side, that is your top view. Okay, so we start with A, or we start with front. Let's say start with front instead of, we start with direction instead of planes. So when you look from the front view, which one of them can you see? So A is perpendicular to the front view, so you just see an edge. B is parallel, so you can see it. E is parallel and H is parallel. So B, E, and H, which are parallel to the front, you can see them. There is no plane that makes an angle with the front view. So all you would see is B, E, and H. So I start anywhere that I want, and I draw B, H, and E. So H, if you look, the dimension is 8 by 1 by 7 trapezoid. So I start anywhere I want, and I draw my trapezoid. So that's 1 unit. This is 4, this is 7, and this is 8. E is similar, but this is 7 and 5, and 2 units height. So it will come to something like this. And B is 2 by 2. And then these guys are all connected together. Okay, now when you do it on a piece of paper instead of on the screen and use rulers, it's going to be a lot better than the mess that I'm making here, because again, it's not easy to draw with a pen on the screen and have a straight, nice, thick lines. So here, this one is your B, this is E, and this is G. Everything else is seen as an edge. Like what? Like A is this top edge, C is this vertical edge, D is this horizontal edge, G is this horizontal edge, and F is this inclined edge. Okay, so that's your front view. Now we create some gap, we consider some gap between the front and top. Or let's go to right for now. Let's go to right first. So if I look at the right view, I see C, which is parallel to right, and F, which has an angle. Everything else is going to be appearing as an edge. So C is parallel, so it appears full size, 3 by 2. That's fine. You have to pay attention to F. How does F appear? Because F appears smaller. How much smaller? So if you draw a right plane here, so if you look at this right edge and draw a vertical right plane, something like this, look. So you draw a vertical plane like that and project all of these points on the right plane. So this point will come right here, right? This point, okay, will come here, and so on and so forth. This point will come here. So it still appears with as many vertices as F does, but smaller. So if you look at the height, it's just 3 units, not this diagonal size. This one just goes up 1 unit. So here I leave 2 or 1 or as many as I want cells between front and right as a gap, and then I start drawing F. So F is going to be 1 unit. This is 2, so we go 2. This other one, which is 6 units apart, so if you count it, the width is 6, so I draw 6 units. As I said, the height of this side is 3, so this guy is 3, so I go up 3 units only. Then I go here vertically up until they meet each other. So this is going to be your F, okay? It's smaller than reality. And C is right above that, 3 by 2. So C is going to look like this. C is easy because it's parallel. So this is going to be C. Everything else is an edge. Like A is the top edge. So A is this top edge. B is this vertical edge. D is this one, G is this one, and E is this one. Okay, so that's your right view. Now, we go to the top direction. So for the top, remember here I left 2 units gap between these two views, so I do the same thing here. I leave 2 units gap, and then from this point upward, I will draw my what? My top view. So I leave 2 units gap, and now start. So if you look at the top, you would see A, D, and G. They are parallel to you. They appear full size. F has angle. So F would appear, but smaller than reality. So if I start with G, G is a what? G clearly you see it is a 7 by 2. So I start G and I draw a 7 by 2. Then D has several vertices, but the width here is 1 unit upward. So we draw that. This is 1. Then you go forward 2 units, so I'll draw that. Then you go in depth 3 units, so we draw that. Then you go forward 3 units. I guess no, that's right. And then you come down 3 units, 4 units, and then go back to where you started, so here. And then A is the 2 by 3, so A is going to be like this guy. F, on the other hand, when you project this, this time you have to draw a top plane. So you can either use the bottom or the top, doesn't matter. So you have to use this plane. You have to project everything onto this plane here in green. So when you project this point, it goes down, projected here. So all you would see is 1 unit. So you can extend this 1 unit, and then you go back 6 units. Here, if you bring this guy down and project it, you only have 3 units, and then you connect. Okay, so now you can say this is F, this is A, this is D, and this is G. Everything else is an edge, like E is this one, C is this one, and B is this guy, H is this front edge. Okay, so this is how you create these views. Again, the gap that you leave between front and right is the same as front and top. As many units as you want, 1, 2, 3, doesn't matter, but make sure they are the same. 1. The other thing that I should warn you is when you draw the top views, some people, when they draw it, they do not stand on the front side and the right. They don't stay here or here actually. They don't stay here and look down so that they can see this. They stay here. They stay on the right side and then they look down. When you do that, it is going to be wrong. What's the difference? If you do that, it actually would look like this. Let me draw it somewhere for you. So it's going to be exactly like this top view, but rotated 90 degrees. So if you do that, you're going to see something like this. So 6, right? And then that is 8, correct? So 4, 5, 6, 7, 8, and 6 again. 8, A, oh no, he's going to be like this. Gosh, it's so hard sometimes to just write with the pen. And then B, and this one. So it would be like this. This is A, this is G, this is D, this is F. So if you look with this person, you would see this, which is absolutely wrong. Because if you bring this guy and put it right here, then the front view and the right view, the top view cannot be vertically aligned. This is only 6 unit wide, this is 8 unit wide. Okay, so you cannot bring this and put it on the top of the front view. They are not vertically aligned. Okay, so pay attention when you draw the top view. You have to stay on the front side and look from the top to get this one. So this here, this person is in the right location. This is good. This one is not. And you can see everything can easily be transferred, right? If you use projection lines, you clearly see, for example, if you look at the boundaries of F, correct? Look, the left of F and the right of F, let's see. So the right of F is here, the left of F is here. You see? F is between these two vertical lines. Yeah, A, look, it's between these two vertical lines. You see, I can easily see A is below A. Or here, you can go horizontally. Look, for example, C is between these two lines. If you watch that, C is between these two lines. Right? I can go horizontally. Or E, for example, is between these two lines. Here and what? Here. Okay, so alignment works perfectly fine. So we went through this problem, and you can see the views here as well. But I added dimensions to make it more accurate for you. Now, before I go to this one, there are a few things that we need to... did I have two of the same thing? Oh no, actually I have to bring this down here. There are several things we have to discuss. One is third angle projection versus first one. So third angle is the one that we use in the ANSI standard. First is the one that we use in ISO standard. ANSI is the standard that we use in the US. It is also used in Canada and United Kingdom, UK, while first angle is used in Europe, Asia, and actually most other countries. What's the difference? So third angle that we use, what you do is when you unfold the box, as we just saw, we put the front at the center, top on the top, right on the right. Everything logical, everything fine. The symbol for this projection is this guy here. So if you ever see that you have two concentric circles and to the right of them there is a trapezoid, that's the third angle projection. And you know why? Because if you look at the truncated cone inside the glass box, if you look in the front view, you would see two concentric circles. If you see it from the right view, you would see a trapezoid. And so you put the front and the right on the right side. And so this completely makes sense. And this is what? This is the symbol of third angle projection we use in the US. Now, in the ISO standard, which is used in Europe, the projection method is called first. What's the difference? So what you do here is, if you still have the same truncated cone inside the glass box, what's the difference? So here, if you basically look from the front direction, okay, if you call this front direction and that is right direction, the order of arrangement is opposite. So instead of right view being on the right of the front, you see it is what? On the left of the front. Or here, you can see the same thing. The right view of the object is placed on the left of the front. And the top view is placed what? Below the front. Okay? So the difference, if I want to summarize it for you, is basically in the third angle method projection that we use here, and we stick to this, the arrangement of the views is front, right, and not like that, top. Okay, so this is front, this is top, this is right. The symbol of that, you saw, it looks like this. In the first angle projection, we do opposite. We put the front at the center, but the top view goes below and the right view goes to the left. And the symbol for that is exactly mirror image of that. So the right view goes to the left of the front. Okay, so I don't really like it. This is counterintuitive, so I would like us to stick to the third angle, because top should be above and right should be to the right, not opposite. But just wanted you to know about this. So if you get some drafting from Europe, or you want to send something to Europe, you know there is one difference between the two standards. Now, in addition to visible lines that we showed in this example here, which show thick solid lines that show visible boundaries, we learned in the first video that when you do these multi-view orthographic projections, there are more lines than just simply thick solid line. Like what? So there are some other lines. For example, one of them is what? Hidden features. If you have something hidden, if you remember, the way to show it is using dash lines. For example, if you look at this object and you look at it from the front view, so if you look at it from the front view, the visible thing that you would see is this L-shaped surface. But you cannot see this basically square cut here, this pocket. So the boundaries of that are shown here and here. You cannot see this cut. So the top boundary of that is overlapping with this, so we don't show it, but the bottom boundary of it we show here. These two holes, you can see them, so you have this small visible circle. This cut here, we call it the countersink hole. This countersink hole we cannot see, so what? We show it with invisible dash lines. So wherever you have a feature that you cannot see by just looking into that direction, you show it with what? With dash lines, okay? And that is extremely important. So when we go to our next example, which is this guy, there are some hidden features, and we have to not only use visible solid thick lines, we have to also use dash lines. The other thing we have to pay attention to is curved surfaces. So whenever a flat surface is tangent to a curved surface, we do not need to show any visible lines between them, okay? So we can see that example here, that this flat surface becomes one and tangent with the curved surface. So here I do not show any visible edge, because visible edge means there are two different surfaces, or there is a break between them, or the angle of the tangents are not the same. In calculus, you said at that point there is no derivative. So you can see here, there is a sharp edge, and they are not tangents, so I have to show the edge to say that these are different surfaces. But here, since at this vertical position, they become one, they become tangent, so you do not need to show any visible edge. Also, if there are fillets and rounds, you have to show them, right? So here, this edge is filleted, so I show it with this small radius here. Or here, these edges that are rounded, these external edges, I show them here, right? So you can see the fillets here, here, and here, and then you can see the rounds here. The other thing is center lines. So if the object is basically symmetric about an axis of rotation, then you have to show that. You have to show the center lines, or the axis of symmetry. Now, if it's a cylindrical surface like this, if you see it from the direction that it appears as a circle, then you know circle has infinitely many planes of symmetry. So you're not going to show all of them here on this top view, and from all of those you just show two of them that are perpendicular to each other, one horizontal, one vertical. When you look at it from the side view, then there is only one plane of symmetry, so you only show what? One axis. Okay, so from the side view you show one axis. From the top view, if top view is the one that appears as a circle, you show what? You show two axes. And for axes you use what? Dash dotted line. Okay, so one of the dashes is longer, the other one is shorter. Okay, long, short, dash. We call it dash dotted line. So we use this one. The other important thing is when these two dash dotted are forming a cross at the center of this view, the small portions should cut each other, not the long ones, or not a long and a short one. That is a mistake. Okay, so when you do it on the paper, you have to pay attention. When software does it for you, software knows what to do, because they were pre-programmed by engineers like you, who told it, hey, at the centers there is a small cross, not a big or not a short long kind of cross. So basically what I mean is you should not have something like this, that this is a circle and then the axis of symmetry, they cut something like this. So you have a long one, a short one, a long one, a short one, a long one. And then here you have a short one, a long one, a short one, a long one. So this is wrong. Or if, on the other hand, you can do this, use the long one. This is also wrong too. Only the small ones should cross each other at the center. You have to have a small cross at the center. Okay, so here you can see different center lines for different cylindrical surfaces. One other thing you have to pay attention to is the half cylinders. Okay, if you have half a cylinder, then you do not have those infinitely many planes of symmetry. You have half of them. And so instead of you using two dash dotted lines, full dash dotted lines, and forming a cross, what you do is you show one dash dotted line completely, the other one you just show half of it. Okay, so as you can see, this one is half. It does not extend beyond the center upward. This one does. It goes left and right. This one does not. Okay, so you show basically half of everything, or 3/4 of everything of the axis of symmetry, right? So again, I emphasize that for you here. If you have only a semicircle view, then you just form a small cross here, and then line, 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 and then this one you do not continue. You just keep it as is. Okay, so that's the difference. Now, one last thing we need to know before we do more practice is order of precedence or priority. If at one position you have more than one type of line, so let's say a visible and a center line overlap, right? They are coincident. Which one would you show? The order is this: always visible first, then hidden, then center. For example, here, if you look at edge B, which is on the right view of this object, at edge B, which is this location here, you have a visible, but if you look behind it, there is the center line of this hole. So at B, there is a center line, but you're not going to put that center line also on B and extend it even outside the object. You just show the visible, that's it. If you look at edge A from the top view, which is basically this one, right, the same edge, when you look at it from the top view, you have A, which is a visible, and what? What else do you have on A? Yes, if you go down, you see it is going to be the left edge of the circle. So there is a hidden line right below the visible, and again you show the visible. And if you look at C, what would you have? If you go down, you have the center line of this hole, and then you have what? The invisible for this edge at this corner that goes all the way to the rear plane. So there is an invisible to show that edge, and there is a center, and you show the invisible. Okay, so order of precedence is extremely important. Now, there are two more practice problems that we're going to go over. One of them we'll do here. The other one we'll keep for inside the classroom, plus more practices. So first, let's do this one. This one, all the dimensions are given for the isometric, and we are going to do that. So if I bring that over here, okay, now that's a big mess, so I have to bring another paper. That is not worth to clean it. So here we go. I'll bring this guy down, and let's create the views of this. So here there are several planes. Again, you can name them. This is A, this is B, like this is C, D, E, F, G, and then inside of the circle, but we don't really need to name. It was just for clarification. So if you look in the front direction, you can see this polygon. That's all basically that you can see, and the circle. Anything else will be hidden. And if you count the number of squares, so you see the width of the part is 8 units and the height is 6. So you start anywhere that you want and you go up 6 units. And then in the width you go 8 units. Then you go up 3, you go forward 6, right? So you go 6, you go up 3, and then you connect them diagonally. Like that. So that is this. Then you have the circle. Here we assume that the diameter of this is 2 units. So let's say phi. We'll see phi means diameter. Phi is 2 units. And let's say the center of this, okay, the center of this is 1.5 and 1.5. Okay, so this from here and this from here, they are both 1.5 and 1.5. So we come here and then we draw a circle with 1.5 units or 2 unit diameter. Similar to this kind of, right? A little bit bigger. Something like that. Okay, so we make our circle. Let me make it a little bit darker. So that is my front view, but there are some stuff missing. What is the only thing I cannot see? I cannot see this surface here. I cannot see where this pocket ends. And this cut extrude or pocket ends basically 2 units before the left edge. So it ends here. So at this point, I have to draw what? A hidden vertical line which tells me where is the end of that curved pocket. The rest of the boundaries of it, the top one, this one, the bottom one, they fall on the top of the visible lines. So we don't show them. We only show this edge of it that we cannot see. So that is my front view. Also, since there is a symmetry here, so I have to add what? An axis of symmetry. And since it's circle, I have to add a cross, right? So I add one here, one here, one here, and one here, right? Let me see if I can make it a little bit cleaner. This is not my preference. The problem is there is no traction here. Let me not mess up with the circle. Let's just keep it as is. Don't need to make it darker. Okay, so this is your front view. Now you can see everything else. Now when you look at the right view, in the right view you can see these two inclined ones smaller. These two you can see full size. You can see this cut. The only thing you cannot see are the holes. If you look at the dimension of the front, the right of the object, it is 6 by what? 6. Okay, so you draw 6 by 6. You leave as many units as you want, gap between the front and right. So here I leave 2. Then I come to the right view and start drawing. So we go up 6. Let me see if I can draw a square to make this cleaner. So I go a 6 by 6. There we go. Maybe I can make this thicker. Can I? No. Okay, so I do a 6 by 6. And then I just make it a little bit thicker just to make sure you can see it well. And then these two guys are both 3 by 2, so they go like this. And these, when projected onto the right plane, they would also be 3 by 2. So they would appear like that. The top portion is the inclined one, the bottom portion is the flat one, and similarly on the right side. Now, this curved surface would appear as the rectangle. Those circles you cannot see, diameters are 2, center is 1.5 above, so 1.5 above, 1 below, 2 unit diameter, so you can project them also horizontally and see that these guys are going to be what? Those 2 holes that I cannot see. They appear invisible to me, so I would draw them invisible. The other thing I have is the center. This object has a plane of symmetry passing through the middle, so in the middle I have to create what? A center line. Okay, so this is my right view. Finally, top view, again, we have to stay here and look down on the front side and look down. So I would see this C plane and these two basically smaller than real size. Again, I cannot see the holes. So the same 2 unit gap I had between front and right, now I leave between what? Between front and top, and I would start drawing. So 6 units, another 6 units, and 6, 2 more for the inclined ones. Go up 2, come down 2, these 2 guys. Then go back 4 units inward. Right, you see 1, 2, 3, 4, and then an arc with a diameter of 2, semicircle. Like that. And then the boundaries of this inclined surfaces. So this is your top view. Now we have to add the hidden holes, which again, you see that they are basically here. And here. Same thing here. And now, since this part has first an overall axis of symmetry, so we add that, plus we have a circle. So for the circle, we formed a small cross. And we continue. Now, we don't need to continue here, but since your object does have a what? An overall symmetry, it's okay if you add that in this case. So this rest of it does not mean that's for the arc, it is for the entire part, the plane of symmetry for the entire part, and also the holes, right? So the holes, they have axes of symmetry. So this is one, and this is one. Okay, so this is how you do the three views. The other thing we missed was the axes for these holes in the right view. So right view, we have again the symmetry here. So we have to show the same thing on the right view. Okay, so this is how you do the three views for this object.